Welcome to part 2 of 3, where we talk about this Foundations of Math outcome 30.7. Now in this one, we're going to be talking about logarithms and exponentials. Now of course, I do it opposite. I do exponentials and logarithms. Exponentials are kind of the easier one to understand. Logarithms have some good applications to them as well, but we'll talk about that. Again, the focus on this unit is looking at the characteristics as well as being able to use the technology to do some graphing. Of course, looking at characteristics of both exponential and logarithmic functions were from their equations. Of course, in order to demonstrate mastery, being able to demonstrate your understanding of exponential and logarithmic functions. And these are some of the different ways that can be done. So for our first section, we're going to just look at strictly the characteristics of what an exponential function is. I know that I use it slightly differently than what our approved textbook is. I tie a lot into the pre-calc 30. So I reuse some of my notes and such. So for example, exponential functions are functions that go up or down by a set proportion. The graph of an exponential function, that doesn't actually need to be capitalized. I'll fix that. Such as y equals c to the power of x is increasing when c equals 1. So c is known as the base. The textbook uses b as a base, but because some people do take pre-calc 30 and foundations 30, I stick with a base of c because the b indicates a different value. But no matter what, it's still dealing with the same thing. The base, as long as the base is greater than 1, you have an increasing exponential. If our base is in between 0 and 1, we actually have a decreasing exponential. And it's neither increasing nor is it decreasing when our base is equal to 1. From the graph, you can determine characteristics such as domain, range, any intercepts, and any asymptotes. So for example, this is an increasing exponential graph. The base would have to be greater than 1. So it could be 2, it could be 3, it could actually be 1.000001. As long as it's greater than 1, you have an increasing exponential. Whereas you have decreasing exponentials if our c is in between 0 and 1. So it could be 0.000002 and to 0.9999999, obviously on forever, but any value that's in between 0 and 1 creates a decreasing exponential. Now we had talked about our exponential growth, especially when we talked about it in Science 10. And actually, that's a mention that I make on the backside. But increasing is talking how things just are going to constantly go up and go up and go up. So what we're going to do is we're going to tie some of our exponential rules into this, and we're going to determine some points. So we're going to determine this table. So some nice numbers to work. We're going to do domain and range, x and y intercept if they exist, where the graph represents an increasing or decreasing function, and what the end behavior of the graph would be. So first off, we have the equation y equals 4 to the power of x. So I'll just get rid of that equation. Now we could use any kind of value for x. Some really nice ones to start using are -2, -1, 0, 1, and 2. So if we go back to our exponent laws, back from grade 10, if we put -2 into here, 4 to the power of -2, because we have that negative exponent, it means that we'd have to take the reciprocal of the base, and then we would be squaring 1/4. Now to square 1/4 means we'd be squaring the numerator and squaring the denominator, which means we would have 1/16. Of course, back to a decimal is 0.0625, but 1/16 just works out a lot nicer. I like fractions. if we used 4 to the power of negative 1? Well, that negative, just a negative, means that we take the reciprocal of the base, being raised to the power of 1, and 1/4 to the power of 1 is just 1/4. Of course, if we did 4 to the power of 0, which would be the next one, anything to the power of 0 is 1. And then these ones would work out really nicely. 4 to the power of 1 is 4, and 4 to the power of 2 is 16. So I may have to do a little bit of rearrangement on here. For example, I'm going to do this one first. Is this going to be representing an increasing or decreasing function? Well, if we look at it, our x is -2, our y is 1/16. When x is -1, it's 1/4. 0, 1, 1, 4, 2, 16. Well, obviously, you can tell that this is going to be increasing. Why? Because the y values are increasing as you move along the x-axis. At the same time, we could also look at what our base is. That base of 4 being greater than 1 means we have an increasing graph. Because it's an increasing graph, we can see from here, all of our increasing exponentials are going to look like this, which means it's actually going from quadrant 2 to quadrant 1. So that'll be the second thing that we'll talk about. Then let's talk about x and y-intercept, and then we'll do domain and range. So our x-intercept, special thing about exponentials is there is no x-intercept. This graph will continue on. It will get dangerously close to our x-axis. It gets smaller and smaller and smaller, but would never actually hit the x-axis. So to indicate that we have no x-intercept, we would write the null set. What our y-intercept? Well, our y-intercept happens when x equals 0. That's literally the definition of the y-intercept, is when x equals 0. And if our x equals 0 here, y value is 1. Our domain, because we can tell from here that our x does keep on going down to -infinity, and this does keep on going over to the right, which means positive infinity. Our domain is represented by all the real numbers. Our range, being our y values, because there's no x-intercept, it's going to get dangerously close to our x-axis. It would never actually hit 0, but it does keep on going up. Help illustrate that, we would say that y is such that y is greater than 0. We would not write equals to. Y would be an element of the real numbers. If we talk about the next one, again, we'll use the same x values, -2, -1, 0, 1, and 2, just because they're really nice and easy to work with. 1/2 to the power of -2, well, as soon as we have that negative, it means we would be taking the reciprocal of our base. The reciprocal of 1/2 is 2. Taking that reciprocal just gets rid of the negative, and then 2 squared is 4. We do the exact same thing for the -1, which means we take the reciprocal of the base, and 2 to the power of 1 is 2. Of course, just like we had done over here, 1/2 to the power of 0 is just going to be 1. 1/2 to the power of 1 means 1/2, and 1/2 to the power of 2 means that that 2 gets distributed onto the numerator and denominator, which means that we would have 1/4. Of course, it would be the same thing here, but 1 to the power of 1 is 1, and 2 to the power of 1 is still 2. So that number is not going to be changing. If we talk about our characteristics here, we can see that as our x's keep on going on, our y's are actually getting smaller and smaller, which means that we have a decreasing graph. Another way we can tell that is by seeing that 1/2 is a number in between 0 and 1, which means it is going to be a decreasing graph. The special thing, though, is that all of our other characteristics, our quadrant end behavior, is still starting in quadrant 2 and ending in quadrant 1. Does it have any x-intercept? No, it's going to keep on going. It's going to get dangerously close to the x-axis, but it would never actually hit. Which means we do not have any x-intercepts. Well, we can tell that because x equals 0 here, our y-intercept is y equals 1. Now, when we do our section 2, we'll see that this does change, but we'll deal with it. For our domain, well, this is still going left and this is still going right. But because it doesn't hit the x-axis, it's all of our values that are greater than 0. So our domain and range also do not change. So let's just write that down. And there we have our characteristics, explained by the equations and even by a table of values. So where that starts leading us into is some of the application of what this really means, what we can do with it. So what function of the form y equals c to the power of x can be used to describe the graph shown? Well, it means what is c? What we're saying is we have 3 different answers here. All of our coordinates go x comma y. So we have 3 things. We have 16 equals some c value to the power of our x value. Well, what number to the power of -2 gives you 16? At the same time, it's saying what number to the power of -1 gives you 4. The last one is a little bit redundant because it's asking what number to the power of 0 gives you 1. Well, every single number. So this one's not really a good it's not a good one to start. So we're not even going to consider it. Now we can go a little bit by trial and error. But at the same time, if we look at our patterns of what we've been doing up here, well, anything to the power of a negative means that we're taking the reciprocal of a base. Well, the reciprocal of what number gives you 4? 1/4. 1/4 to the power of -1 would give you 4. Likewise, 1/4 to the power of -2 by taking the reciprocal of the base, 4 to the power of 2 absolutely gives you 16, which means our equation of this graph is y equals 1/4 all to the power of x. Now you can absolutely write brackets around it. I would certainly encourage you to do it. is it means that you're going to be taking this entire base to the power of x. It looks a lot neater when you do have the brackets, especially if you have a fraction. If you have, say, just a number, well, you're fine. So like I had mentioned, we had talked about some exponential growth in Science 10, because growth, we'll be talking about an increasing graph. But if you have your base in between 0 and 1, it's known as an exponential decay, where you'd have a decreasing graph. So in our example, we have a radioactive sample of radium, so radium-225, has a half-life of 15 days. The mass, m, in grams of radium-225 remaining over time t in 15-day intervals can be modeled using the exponential graph shown. This graph. I was saying we have a certain amount of mass, and over time, every single 15 days, so the first 15-day interval, it decays to be half of the size. Because we have time on the x-axis, and we have mass in grams on the y-axis. So time, grams, time, grams. But each of these time are 15-day intervals. So one 15-day interval means 15 days. Two 15-day intervals means 30 days, 45, 60, and so on. The first question is, what is the initial mass of radium-225 in the sample? And what value does the mass of radium-225 remaining approach as time passes? So the first question is asking, what is the initial mass? Well, initial mass is asking, when has no time progressed? So when our time is 0, we can see that the mass is at 1.0 grams. And what mass does it approach? Well, as the time slowly progresses, it seems like the mass is going down, down, and down, and down, and down, and it's slowly but surely approaching 0 grams. What would be the relevant domain and range on this function? Well, we can't say that our domain is all real numbers because we can't go back in time. But we are starting at a time of 0, and it technically does go to infinity, which means that our domain, now g, is it grams? No, it's time. Our domain, which is on our x-axis, is talking about time. Well, our time is 0 is our lowest value. It does hit 0. But it does continue on forever. Now, traditionally, yeah, I'm not going to write it like that because that looks kind of really bad for me. The time is always going to be greater than or equal to 0. Yes, time is still an element of the real numbers, but just meaning that time starts at 0 and goes on. Whereas our range is talking about grams. So what grams is it talking about? Well, it's approaching 0, but its maximum mass is 1 gram. We would always want to write our lowest value first. So because it doesn't actually hit 0, because we're saying it's modeling an exponential graph, 0 would be the lowest value, but it does actually hit the 1 gram. It hits every single value in between. So what we're going to do is we're going to write the exponential decay model that relates mass remaining to time in 15-day intervals, which means it's actually just asking, what is the equation? Well, the beautiful thing about the equation is this. Y is still going to be our y-axis. X is still going to be our x-axis, which means when we put it into our equation, our wet mass is our y value. So grams. X, well, the thing on our x-axis is our time. The last thing we need to find out is what is our C? Well, we're trying to find out what is our base. The great thing about exponential decay or even exponential growth models, it's kind of, well, for decay, it's really specific. It's asking how much remains. Now, when I write that, I'm not saying how much remains at the very end. I'm talking about after each time period, how much remains. It does have to be a proportion. In this case, it's a half-life. Every single 15-day interval, the mass is becoming half of what it was before. After 15 days, that 1 gram has become half a gram. That half a gram then becomes a quarter of a gram. That'd be an eighth, a 16th. Our proportion, our base, is actually just a half then. And that's it. All right, last thing. Estimate how many days it would take for that radium-225 to decay to 1/30th of its original mass. Well, because we have the equation, what it is essentially asking is when is the mass 1/30th, or as close to as possible. This one can be done relatively well as a trial and error because it's really nice to deal with. But we know that 1/2 to the power of 1 is a half. 1/2 to the power of 2 is a quarter. 1/2 to the power of 3 will be an eighth. And hopefully you see where I'm going here, because that 1 goes to the power of 3 and that 2 goes to the power of 3. 1/2 to the power of 4 is 1/16th. Not quite 1/30th. If we go one more, 1/2 to the power of 5 is 1/32nd. Because it's 1/32nd, our T is 5. For some reason, I want to write 15. That's not right. Now, the last thing is this T is 5 15-day intervals. Which means it's 75 days. There we go. That's what we're talking about when we have either an exponential growth or an exponential decay, increasing or decreasing exponentials, which means you can have some fun.